So hi everybody, it's 8 p.m. GMT, and I would like to welcome you to VSAONLINE talk. Today, I'm very happy to welcome Paxon Frady from Intel Labs. He will talk about vector algebras. So now I'm reading from screen on Leihi 2. Before I leave the floor to him, I want to maybe repeat my message from the mailing list and make an announcement about plans to organize a workshop, more of a really kind of get together in Luleå in the beginning of June. So now the plans are, well, compared to my original mail, so it shifted 2 days to the future. So it's 14th to 15th of June. So this is the current plan. So 14th, 15th of June. So please consider attending the Midnight Sound workshop in Luleå. So I don't know if I can guarantee clear weather, but definitely it will be very bright. And I hope for really great discussions. All right, so without any further delay, Paxon, welcome.
Okay, cool. Yeah. Hey, hi everyone. Thanks for having me, Evgeny. And yes, so then today I'm going to be talking about the things I've been doing, getting ready for Leihi 2 and building a bunch of processes and a library effectively for doing vector symbolic architectures, as well as just normal linear algebra and those types of things. And so as like from a bird's eye view, we're working on Lava, which is our software framework. And essentially Lava contains a lot of these libraries we're developing that have in them a bunch of functional modules. And the hope is that we can string all these things together and build complicated, sophisticated neural network algorithms. And so then there's a bunch of packages already for doing IO or for doing deep learning or for doing optimization. And what I'm going to be telling about is the VSA package, which is mostly for doing VSAs and doing linear algebra and almost like a substrate of everything else. So the most rudimentary concept that I'm building on in the library is just the use of these graded spikes. So Leihi 2 now has the ability to send what we call graded spikes, which include a package of 24 bits. So you can encode into the graded spike, you know, a non-binary number. So you have 24 bits of resolution, and then the whole chip can do basically fixed point calculus. And so essentially, when you think about fixed point representations, usually what that means is that out of the 24 bits, I'm going to say, in this case, the fixed point base is 12, which means whenever I do a multiply, I'll do a multiply and then a shift right by 12. And so all that means is that the number 2 to the 12 really is like the number 1. So like, yeah, so 2 to the 12 is like 4096, but in the fixed point math, that just means 2 to the 12 is like 1. And so then you're just, you know, moving the decimal point of these integer representations. And so that's how we basically are going to encode all the numbers with fixed point values. And the base can change, but 12 is what I'm going to be starting with for now, for various reasons. And then the key kind of process that underlies a lot of the modules I'm going to tell you about is just this like thresholded vector process, right? So this is just like supposed to be the most standard vector representation that you can instantiate on Leihi 2, and essentially it's just, gets a weighted sum, like a dot product on its input channel, then has a mechanism for thresholding the inputs, and basically then it's going to output the graded spike value so long as the value is greater than the threshold, and both positive and negative values. So there's also like more nonlinear functions we could add. I mean, we can do almost anything. It's pretty awesome, but this is sort of just like the basic vector representation just for linear algebra. And one of the big things I've been working on, which is like really pretty mind-bending, honestly, is just a way to represent and normalize vectors. And for a lot of the applications in vector symbolic architectures, or just almost ubiquitously in any type of linear algebra context, you're going to need normalization. And the challenge with normalization is that Loihi 2 does not have a divider circuit. And so we had to do some fancy things to figure out how to compute the normalization factor. But we start with this other fancy neuron model that's encoded. So this is all programmed into Loihi's microcode engine. And in this case, this neuron model looks like a thresh vec. So just it still gets a weighted sum as input, and it will output a thresholded value in the graded spike, but it also has a sort of secondary channel. So it has a second input channel and a second output channel. And essentially what it's expecting on its second input channel is a normalization factor. And what it's going to output on its second output channel is actually the squared value of its coefficient. And then there's also this timing thing. So because of the way the spikes work and the way the timing works, there's a slight delay. So the way this works, well, I'll explain that in a second, actually. So that's just like the idea of the norm vec, right? And so then there's another neuron model, which is right now just called FP inverse 24. So this is like for fixed point inverse square root algorithm with 24 bits. And basically this is something people came up with in like the late 80s, early 90s when they were making the first three-dimensional video games, and we're still using fixed point math and building these graphic engines with fixed point representations. And again, they had the same problem of these early chips. It was that they didn't have dividers. And so there is an iterative algorithm based on Newton's method that allows you to approximate the inverse square root without needing to do a division. And so this is kind of like the Python implementation of this algorithm. But basically you have to look up a value from a lookup table. So that's what's stored in this y_est. And then you just do some multiplies and right shifts in this iterative loop for a couple of iterations, like 3 or 5 is all you need, really. And then it computes the inverse square root. So the idea is that this process expects on its input channel the sum of squares. So the outputs of all these norm vecs are on the second channel, it squares it. And so then all the neurons in that population will be summed together and go into this essentially individual like inhibitory neuron. And then in the microcode of this neuron, it implements this fixed point square root algorithm. And then it outputs the normalization factor. So it outputs 1 over the square root of the input. And then when you go back to norm vec, it gets in this value. And then inside of norm vec, it will multiply the square root factor with the input, the normal pipeline of inputs. So then, yeah, so then this makes a bit of a little network, a normalization network. So yes, your normal input channels come in here. They go through normvac, and then inside of normvac, there's this timing issue. So like this is something maybe I would love some feedback on, but this is sort of the solution we've just done for now. But basically, yes, this value A is then stored inside of this process in a little buffer. So it's held in a little memory buffer. But then it first is sent out sort of immediately as A squared to the fixed point inverse network, right? And this takes a time step. And then the computation of the inverse square root happens, and then that's sent back, and that takes another time step. And then on 2 time steps later, the value buffered of A is then extracted and then multiplied by the normalization factor, and then this gets output. So you put in A, and 2 time steps later, you get the normalized vector. So that's the structure of just how to do normalization. And then, so that's just kind of basic linear algebra. And of course, there's already, I didn't mention the dense, but like there's these, dense weight matrices that are very, I'm sure everyone, it's a normal weight matrix, but that's kind of standard already. And so then, yes, so then we want to do vector symbolic architectures. And this is just my VSA overview slide, but of course we need to implement things like dot products, which is already done with dense, and we need to implement the binding operation. And so that's what I'm basically going to tell you about how we're doing now. And we've settled on actually 2 frameworks that are going to be available on Loihi 2. And one is the sparse block code. So basically the vectors are, again, just random vectors with 1 hot elements. But if you put them in superposition, of course, then the graded spike values are going to be used as part of the superposition. And then there's a block local circular convolution is the binding operation in this model. So I'll tell you how we're going to implement that. And the other representation that's going to be available is the Fourier holographic reduced representation implemented with spike timing codes. So basically, the complex numbers in this framework are going to be implemented with this oscillatory spike timing mechanism that we invented. And then you can do also the binding operation with special microcode neurons that I'll describe as well. So then the Blava VSA package also at large has some organizational concepts as well. So there is just basically one idea of like having frameworks where essentially processes that are compatible with each other are just packaged together and put into just like a namespace so that they're easier to access. And then there is this concept of networks, which are just these like modules of processes like the normalization network that are just common and just put together as like another layer of syntax. And what's nice about the networks as well that we're working on is that they have this algebraic formalism, and you can simplify sort of the coding with this operator overloading. And so basically then if you want to instantiate some sparse block vectors, you can create a code book, and you can like instantiate the weights, and then you can instantiate neurons to represent the values, and then you can use this like mathematical algebraic syntax to essentially connect the networks together. And so this will take the input, multiply it by the code book, and send it into this neuron population. So then the general idea of the block code is, yes, there are the atomic vectors have essentially one active element per block. And so then you can see here just very simple variation of the block code. And then essentially, of course, when you add them together, there's just superposition, no big deal. But then when you bind them, what happens is blockwise circular convolution, or basically another way of thinking about it is the index of the active elements in the block are added together. And so, yeah, so this is basically 1 plus 8 equals 9 and stuff like that. And then it, of course, also wraps around the block. So if the sum is kind of, it's like modulo the block size. So that's just like what the binding operation is. And then, yeah, so I point you to, of course, Leho's original work on this, as well as our more recent work with this sparse distributed representations paper. So if you want to learn more about the block code, just look at this paper, and we show how the bindings invertible and other important connections to the rest of the VSAs. But then, yes, again, there's like a network module called a sparse block deck, which sort of has the VSA parameters, like you need to know the block size, so that is stored in this module, but then effectively it's really implemented as these threshold vectors, which are the kind of, again, the basic element. Okay, so then in the sparse block code paper, we describe the binding operation, which again is this local circular convolution, but another way you can express it is as the subsampling of the outer product. So basically the idea is that these blue neurons are sort of is input A and input B going down, and these crosshairs actually represent the outer product. So essentially the activity of 2 neurons is multiplied at each of these crosses. Excuse me. And then some subset of these entries in the outer product are then integrated by one of the output neurons. And so basically you need to do this multiply and then add some numbers together from the outer product. And yes, and then so we made this in the microcode. And this is then again a very basic element, which could be used for other things besides the binding operation. But essentially, this is a neuron model where it has 2 input channels. So basically 2. You could have more than 2, but in the context of binding, just 2 neurons are coming into one prod neuron. And essentially then in the microcode, it's going to multiply these 2 numbers and output the product with the fixed point shifting. And then what happens to make the binding network is there is another kind of, a network layer that wraps around prod neuron as well as all the weights. So then there's particular weights from the 2 populations just that define this outer product structure. And then there's this intermediate layer of these multiplier neurons, and then another set of weights that do the accumulation of the outer product into the output vector. And yeah, and so then again, you can use normal syntax to instantiate a network like this and connect it, but again, as an ease of use idea, there's this algebraic framework where we can just use overload the times operation, and this effectively just creates a whole network behind the scenes and connects it all together. And so these are basically the equivalent statements. So this is like the hope of the algebraic syntax making things a lot easier. Okay, so then that was the block code, and then there's also then the spike timing based code with complex numbers. And so essentially the core idea here is that with intrinsically oscillating neurons like resonant fire neurons, we can do all the complex valued matrix calculations, and it's actually quite efficient to do on the chip because it's only like these like neuron models. The resonating fire neuron models are just neurons with two state variables. So there's sort of like a real part and an imaginary part, or if you think about it as like a RLC circuit, then there's like a inductor, so just like or it's like a harmonic oscillator, very, very basic. But the point is that then these neurons will spike when their state variables are both when the voltage is essentially above the threshold, but also there's this condition that the sort of phase of the oscillation has to be at zero. So when it crosses this zero line is also it's part of the spike condition. But when you put those together, the complex matrix algebra is very straightforward. And basically the idea is that then the timing of the spikes is the phase of the complex number. And then the magnitude of the complex number is actually carried by the graded spike. So you can actually have not binary complex numbers by putting the amplitude in the graded value. And then you can also then need these complex valued synaptic connections. So essentially then every synapse has a real part and an imaginary part. And so then this can encode a complex valued weight. And essentially whenever a spike arrives, it's going to cause a jump in the postsynaptic cell based on the weight of this synapse, right? So this spike causes the cell to jump a little bit down and right. And then this spike has a different synaptic weight, and it causes the membrane potential to jump up in the imaginary dimension. And so then if the spike timing code and like the synaptic weights are all coherent, then you'll get this coherent addition of these inputs, and then this will lead to a large oscillation amplitude, and then like if it's above threshold, it'll spike, right? So that's like the basic mechanism how to do the complex dot product with the spike timing code. And so then there's a process then in Loihi 2 for making the resonating fire neurons. And essentially, yes, the resonating fire neuron is just basically a harmonic oscillator. It has a decay parameter and a frequency. And then it also has two input channels, right? So it has a real input channel and an imaginary input channel. And then, so then there's a microcode neuron that executes all this, and it outputs graded spikes. So if the spike's above the threshold, it will output the spike at the appropriate time, and then it puts the amplitude of the oscillation into the graded spike. So it encodes the magnitude as well. And so there's a simple demo I have now too that just shows you how to make a bank of these resonating fire neurons. And so basically if you just allocate a bunch of these resonating fire neurons with different frequencies, then you pipe in a audio signal, they will naturally just oscillate from the audio input, and more or less their amplitude of the oscillation computes the Fourier transform, or well, more specifically, the short time Fourier transform or the spectrogram. So it's like kind of happening in time. And then the spectrogram coefficients are output as these spike timing codes. So here you can just see there's just someone saying some speech commands, and this is just like the spike timing representation of the RF neurons, but again, the spikes carry amplitudes as well. And so then here I've tried to make a little bit clearer visualization of the spectrogram and the spikes. And so this turns out to be almost exactly, I mean, there's a lot of ways to compute a spectrogram, but more or less this is like an exact way of doing the spectrogram with a spike timing code. Right, and so then there's also complex synapse connections, but the complex valued synapses are really just two real valued synapses, and so there's a network motif where it takes in the graded spike timing code, defines a real valued weight and an imaginary valued weight, and then these can get put into the resonating fire neurons to compute like complex valued spatial temporal filters. And finally, there's the binding operation, and in here, the the idea of the binding operation is in the complex framework. You want to multiply two complex numbers, and so when you do that, you of course multiply the amplitudes, but you also add the phases, and so adding the phases in the spike timing code requires it's a little bit trickier than it seems at first, but ultimately we've come to a solution and also a microcode model, which is just this phase shifter neuron, and again, the neuron just accepts two inputs of two of these spike timing codes, and essentially what it does is it has like an internal clock, and essentially whenever this clock reaches the threshold, it's going to spike, but then the two input spikes regulate this clock. And so one of them will reset the clock, and one of them will subtract or add a value to the state of the clock, which will accelerate it or decelerate it. And this will cause the clock to, take longer, and then the spike will be output later. And this will then cause a phase shift in the spike timing. So this is all just again, put it in the microcode, and this is just sort of like a validation experiment just to show the phase shift mechanism working. The other kind of idea that I want to mention that's not going to be ready too soon, but I think it's worth just talking about to everyone here, which is this idea I've been developing a little bit that hybridizes typical VSAs with also the tensor product representation of Smolenski. And for the general idea of the VSAs was always just to be a reduced representation. And so typically if you kind of take the conventional view of connectionism, then the outer product of vector representations is the correct binding operation. But then the whole point of VSAs was to develop frameworks where you could create a binding operation which wouldn't expand the dimensionality. So of course the outer product expands the dimensionality. That's great because you can also, the thing about it is you can create these more complicated data structures, and you might need lots of bindings to encode, say, a tree or something else. So that's what's nice about VSA, but it's equivalent to doing tensor product. And if you're not worried about the dimensionality exploding, you could also do tensor product. It's not a big deal. But then on the chip, what happens, and what happens in VSA models a lot, is we create these memory structures. So we create these data structures that actually are persistent is the issue. So in this dollar of Mexico example, we build this data register of key value pairs, and these are just held in a vector state, but they're just held in your RAM, right, like a vector. So it's persistent. But on Loihi, the activations of vectors are just spikes, and they're not persistent, and so they come and they go. And so if you want to come back to a data register, it's gone. It's no persistent memory, or you would have to build something sophisticated to potentially hold the vector state fixed as a memory, like an attractor network or something. But this is a little bit, inefficient, and so I've been developing this idea about kind of hybridizing VSA and tensor products. So essentially, when you want to make a memory structure, rather than basically at the last step, rather than putting it into a vector, you put it into the synaptic matrix. And so you can do the whole, say, this dollar of Mexico example by, instead of binding the keys and values, you do the outer product between the keys and values. And essentially, the goal will be to use Loihi's learning engine to store these outer product memories into the synaptic state. And then the synaptic state is persistent, right? Because the weights are just stored and held fixed. And then whenever you want to query the synaptic state, you basically can just unbind the key by multiplying it through the matrix, and then you get out the value. And so that's the gist of the VSA memory. And so, yeah, so when we make, but then you can still make data structure. So you can still make the keys several bindings. So if you wanted to make a tree, then you can still make do the VSA operations to make the pointer to the tree index. And then you would store the pointer and the value into the synaptic memory. And the other good thing about this is that, well, you get actually a lot more capacity because, of course, well, there's a lot more synapses than there are neurons. And so then the crosstalk noise is mitigated because you get the effectively the n squared synapses reduces the crosstalk noise a lot. But then, yeah, you might not want to actually allocate all the synapses either. So you can actually also again, truncate or use a subset of the outer product memory and also still do this and just trade off the number of synapses you actually allocate with the kind of crosstalk noise tolerance you have. And okay, so then just overview of the whole thing is just there's this Lava VSA library imminently coming. The only thing holding us back is just that there are a couple of compiler issues that just I've been hacking around just to test and validate everything. But once these compiler issues are dealt with, which it's not a big deal, everything will be essentially ready to go, and we'll release it soon. But then, yeah, and so then in this library will be a general framework for linear algebra, modules for sparse block codes, and modules for the spike timing variation of the Fourier holographic reduced representation, as well as then, yeah, general packages for organizing everything and kind of making life a lot easier in terms of just where are the modules that need to be put together. They're just like kind of co-localized into these frameworks. And then there will be a lot of these higher level network motifs that will be available. So I just kind of showed you the binding operations, but we'll also have, like attractor memories, hopefully resonator networks, and other like motifs and modules that will be kind of pre-built. And then also, yes, we have this potential for using this algebraic syntax and operator overloading for just making it simpler. But then I think another thing also, if anyone has any feedback, is just thoughts on flow control and timing. And so like, yeah, flow control and timing of all this stuff might be something you really have to think about in a different way. We're definitely trying to come up with sort of a formalism that makes it like a little like sensible, but still something up in the air. So that's all I really have. So thanks everyone for listening and your attention. And I was hoping, yeah, to get some feedback and maybe have a little bit of brainstorming. But then, yes, let me know if you have any questions as well.
Thank you, Paxon. Thank you very much. So now it's time for questions. Please unmute yourself and speak up.
So Paxton, I've got a query about your sparse block code, the Leho model that you're using. You talked about the binding operation. What do you do about bundling, and how do you do the argmax?
Well, yeah, the bundling is still just linear sum. And then it depends if you want to use, so we have just basically like attractor networks or winner take all networks to if you want to just like pick out the winner. But often, you don't necessarily want to remove all the superposition. And then, so then you can also just, normalize the vectors with the normalization network. And there's also the possibility of adding some non-linearities to do something like softmax.
Right, but with the sparse representation, the bundling operation, you have to choose the bit position. If you just add the spikes together, which is essentially what you're doing, you've got to find the spikes that are coincident for the argmax operation in order to do the bundling. So I just want, I mean, you showed how you do the sort of circular.
I think you might be a little bit thinking about the context dependent thinning variation as well. I mean, but usually I would, if you do the argmax or you just pick out the winner, every time you do that, it's going to reduce the information content in the vector. And it's so much that I wouldn't recommend doing this.
Okay.
Yeah.
So in the paper I presented earlier in the session, a few sessions ago, we actually used the earliest time to spike on any neuron. And provided you've got enough bit positions, that works as well as the argmax. So it might be useful to have something that did that.
So you're saying, okay, like the time. But you're saying the timing is the amplitude, right?
I'm just saying that the time of the earliest spike for any neuron. So you're going to have a number of neurons to represent your vector. Yeah.
But see here, like amplitudes are graded spikes. There's no timing. Everything happens all at once.
Right. Okay. So that was just a supplementary question on slide 13. You showed the sparse encoding, and you showed weights as well. So what you're talking about there is again, the other weights, something that are applied to the graded spike.
In this case, the weights are all just one, because it's just structuring this outer product. So basically, right. So this one neuron, has two synapses to this intermediate layer of outer product neurons. And this other neuron has two different synapses to two different neurons, right?
Right.
So then these weights, I don't know what would happen if you made them not one or zero. They're all just binary for this circuit.
Okay.
But basically, it's just like creating this outer product connectivity structure for this intermediate layer, and then again, the weights out are these red lines to the output layer.
Okay. Just one final question, and I'll let someone else ask. You said about with the memory, you talked about storing the weights in the synaptic memory model. Can you store time delays in that model rather than weights?
Can you store time delays? Yes.
Right.
You can store them, but I don't know necessarily what the learning role should be.
Yeah. Okay. I'll think about that one.
But
Thanks very much.
I think you can rewrite the delays. I'm not sure. I'm not entirely sure if the learning engine can rewrite the delays.
Okay.
You can write the delays like from the CPU, but I'm not 100% that you can use the learning engine to do it without. I think you can, but I'm not 100% sure. Yeah, but then you also need to think about yeah, how would you learn? Yeah, like what would be the learning rule? Because the synaptic engine, the learning engine has, you know, the way it works is basically it has these trace variables you can define for every synapse. And so then you would have to basically use these traces to keep track of the delay structure. And then you would want to probably, based on say like the later spike arriving and like the time, the trace, keeping track of the delay from the first spike or something, you would then be able to use those two the trace and the new spike to trigger some learning rule that would then change the delay. But I'm not sure how you do it. I'm not 100% sure that the learning engine can change the delay, but it might be able to.
Okay, thank you very much. Thank you.
Maybe I can insert a short question from my side. This introduction of these graded spikes, so does it mean that you kind of, I mean, this new Loihi chip requires some exact computations, or in any way? So the question is, do you have any sense with respect to kind of energy consumption? So if you do similar operations on kind of traditional architecture, so how much do you win? No, you see, yeah, I mean, yes, actually, and it's not a tricky question. So it's rather, you know.
Yeah, it's very conventional though. Like the core has, I mean, you know, the chip, like, you know, it has a lot of neurocores, right? So that's one thing that's very different, right? It has thousands of cores, but then each core has more or less a language, like an assembly language at this point, and has very conventional computer architecture operations, right? And so it does very conventional things. But I think there's a couple of ways they save energy, and you know, one of them is that yes, you can run the voltage lower, and another thing is just, yeah, you save energy because of the lack of a clock and the you know, communicating by spikes and just having everything co-localized. But I don't know if I'm not sure if like you compared like one multiply operation on a neurocore to a multiply operation on a CPU. Yeah, I don't know if there's like.
But don't you think this is? I mean, this kind of benchmark and some. I mean, something that is needed. I mean, because this argument that neuromorphic saves energy, I mean, it's cool. So having
benchmarking is good and definitely useful. I'm just saying the energy savings doesn't necessarily come from the multiplier, it comes from the communication and the clock.
No. Okay, I'll let somebody else to jump in with questions. Hello, anybody?
If I must.
No, yeah. Oh no. Oh well. Go on.
Thanks for that, Paxon. Paxon, you mentioned right back at the beginning that you wanted to do a bit of a brainstorming session in this. So these are the dreaded more of a comment than a question kinds of things.
Yeah.
There are a couple of sort of the relationship between, let's call it classic VSA, and particularly the slide where you're talking about sort of trying to hybridize VSA with tensor product representations. And you made a couple of comments. There's really sort of two main points to this. One is you're talking about, you know, sending stuff out to weights because of persistence, and that, you know, classic VSAs, well, as implemented anyway on Loihi, have no persistence, as you're saying. It's basically spikes when once they're gone, they're gone.
Right.
But I mean, classic VSA stuff. I mean, from the maths sort of algebraic point of view, really is blind to the issue of persistence. So I think one of the early papers, I think it was the one the Jackendorf challenges thing they did a gazillion years ago, was pointing out that there's nothing in the VSA stuff which says whether a particular vector is represented as a vector of activations of neurons or as synaptic weights. They're just vectors of values as far as the VSA side is concerned. So you sort of have the freedom to separately specify the persistence. But since you were emphasizing earlier on sort of the use of that more algebraic notation to do your programming, I was wondering how you would try to represent persistence or not within that algebraic framework, or is it not possible, or not valuable to do that? Is it just sort of a decoration you put on a particular data structure to say, oh, by the way, this is persistent? So that's sort of one sort of designish kind of issue there. The other perhaps possibly more substantive one is in the sort of the translation between VSA and tensor product kind of representations. So, okay, you've got your tensor product, calling it an outer product. You can decompose that down into a bundle of, well, shouldn't say bundle, down into a set of bindings. So, and you can see this very clearly in Tony's circular convolution binding, that if you divide up the outer product into diagonal strips, effectively what you're doing, if it's a k-dimensional vectors you're working with, you're forming k many VSA Hadamard binding products between one of the argument vectors and k many cyclic shift permutations of the other argument. And so, your classic vector outer product is essentially, it's the concatenation of k many standard VSA bindings. And just as a side note, in circular convolution, you take those k many bindings and then just form the bundle of them to knock it down to one there. So, it seems that it's using binding and permutation. You can fairly easily say, oh, I can translate between thinking of it as a tensor product and thinking of it as VSA. But again, it seems to me that or you could do intermediate things. You could say, I could take, instead of taking k many of these bindings, I could take 3 or 5, and that kind of stuff I've used in the past for doing error correction. So you sort of transiently, or at least in your one place in your computation, do bigger than a VSA, but nowhere near as big as a as a tensor product in terms of number of elements. But once again, I think from the point of view of your algebraic notation, it strikes me that would look fairly messy. To how would you specify that I want to translate this into q many related products, and perhaps put them back again later and sort of keep track of all the index bookkeeping while you're at it.
Yeah, that's a great set of ideas. So yes, I'll again just say that from the high level, like what we explained in the sparse block paper. I mean, Tony Plate knew this in the 90s, right? But essentially, all the VSA binding operations are actually related to the tensor product, and you can see them all as reductions of the tensor product. So so like circular convolution, you do the outer product and then you sum up the diagonals. Hadamard product is just the outer product, and you just take the one on the diagonal of the outer product, right? And then block code, you make another structure. And we played also around with trying to, so like originally we were thinking that, okay, we're just gonna have a vector that's just k-sparse without any block structure, right? And then again, subsample the outer product to make a binding operation. But without the block structure, this didn't work because there were just times where randomly sampling the outer products led to situations where you couldn't invert it, and so like we would get some loss when you tried to unbind some of these not rigid sparse vectors, but then we realized that the Leho variation doesn't have that issue, and so then you get the perfect unbinding and also just the much smaller number of products. You don't have to represent as many, right? Because like a lot of the outer products have no, so you don't have to compute those. Then I guess, yes. So then with I think what you would do, like my answer to how like it would, how this outer product kind of memory structure would, would have to go with the algebraic syntax is essentially this would still work, but you would have to probably just when you create before you use the algebra, you have to allocate all the objects. So when you allocate like U states, like it's going to be this register of key value pairs. Well, in this case, I would probably say it's a a TPR, memory, right? And have like some parameters. And that way it's just like this particular object. And then when you do the kind of algebraic syntax, I guess you could just hopefully just do something like this. And just because it's been allocated as this object, it would hopefully be smart enough to realize that this means actually doing a outer product binding rather than the other kind of binding, right?
Okay, and if the TPR memory had some extra parameters that said, hey, this isn't a complete outer product, it's a partial outer product, then it would sort of remember that in doing the binding, that it's hey, I only need to do 1/k of all these components.
Yeah, exactly.
Or whatever. Okay.
Exactly. Yeah. So then you could just pass in some parameter that says like, I don't want all of the outer product space, I just want like 60% of the diagonal, and then that way you would have to allocate less synapses, and then hopefully it'd be more scalable.
Yeah. Hey, so just since you've been using the plus operator on that second line there, way back at the beginning where you were introducing the algebraic notation, after you had plus, it said addition, and then in parentheses concatenation.
Yes. Yes, because so like it's just funny what happens because basically, like you have to remember that the reason it's concatenation is because, well, like if you say just like output is defined as like weights, and then this is like the dot product E1 plus weights. So like really what these operations are doing are making connections, right? And essentially under the hood, when this happens, basically this is saying E1 dot connect weights, and then it's saying weights dot connect output, and then it's saying should be weights 2, and then B1 dot connect weights 2, and weights 2 dot connect output. So that's like really what's happening.
Oh, so it's concatenation in the threading piping sense. So you're concatenating
Exactly.
the
Exactly.
operations. Okay. Sorry.
So,
Yeah,
so
because I was confused
technically,
there.
yeah. So technically, when this happens, it just concatenates the objects into a list, and then
Yeah.
once this connection thing gets called, it goes through the list and connects each object.
Yeah.
So
So
that's just what happens.
it's composition rather.
Yeah, it's composition, but then
Yeah.
it has the end effect of just adding things. Yeah.
Yeah,
So,
because
yeah,
I was getting confused because I was misinterpreting that. So I
right.
was thinking in the sense of VSA, well, typically, plus you'd use to indicate a bundling operation, whereas concatenation, I was thinking of actually concatenating two k-dimensional vectors to make a 2k dimensional
Yeah, yeah,
vector.
yeah. I didn't mean it
Which
like that.
obviously, no, yeah, okay, because I mean that
Yeah.
the thing is that if you concatenate vectors like that, yes, it gets
No.
you the average of the dot products of the two halves, but it's also binding like as well, because it's got
Right,
a
right.
separate
Yeah.
set of indices. Yeah.
We also explain in the sparse binding paper, we also talk about how you can have VSA superposition, but of course there's, that loses the set property.
Yeah.
But then what you can do, we call this creating a protected set. So you take one set, bind it to a key, take the other set, bind it to a different key, and then you can add them. And now the keys indicate the set, but this
Yep.
is the protected set is equivalent to concatenating the original vectors.
Yes. Yeah. Because
Yeah,
you're binding it to a different set of indices,
exactly.
effectively. Yeah.
Yeah.
Okay. Sorry, I'll get
But
out of
yeah,
everybody's head.
I meant it from like the underlying structure of what happens is like these things get concatenated, and then later the list of things gets connected, and then that's just how addition, because you're really just
Yeah.
structuring the network, and then when you connect two things to one thing, they add.
Terrific. Thank you, Paxon.
Thanks, Ross.
Yeah. Hey, Paxon, so on this Loihi chip, when you have the phasor vector representation, is the timing that you're talking about, is that actually physical timing?
Yes.
Okay. So yeah, so my question is how efficiently does that use the space and time resources of the silicon? So like how long is that so that spike is occurring at some, within some interval. How long is that interval? And could how does that compare to sort of more densely packing, information into the silicon in that time interval? Do you understand what my
yeah, I do. Yeah.
Yeah.
So the time interval is just defined by the frequency of the neurons, and so it's just a free parameter. But
right. And what is that time interval?
It just depends on what your context is, but like it has to. So the thing is like to implement the resonating fire neurons on the Loihi, the chip is discrete and everything's discrete, and so when you try to make a continuous dynamical system on something discrete, you get some errors, right? And so if you try to make the oscillators like in too few time steps, like if you try to make a cycle in like less than 10 time steps, then you get a lot of numeric integration errors. So that sort of limits how fast it can be. But then the other aspect is the reason like I'm trying to get it to work too is because I think we can decompose a lot of the audio and video signals into like basically different frequency channels. And so then you would have basically in parallel VSAs operating on different frequency channels. And so then you might have a variety of these cycle times. And so yeah, like when I do the spectrogram, right, all the RF neurons just have different frequencies. But then if I was going to do like VSA stuff kind of operating on the spectrogram data, yeah, I think you would have to just break it into different frequency channels, or I'm not sure how to like multiplex it entirely. But then, yeah, I mean, but then the range of it, I mean, it's pretty general. And let's see, the complexity, well, it also depends. I mean, it probably, one thing we showed though is that when you just talk about doing this spectrogram, the resonating fire neuron is actually pretty much the most efficient way of computing it. So basically, I mean, it's essentially the same as what, it's not really like just having a little oscillator isn't really different than what people have always been doing with Fourier analysis, but effectively like there's essentially two ways of computing the spectrogram. One is like you do the fast Fourier transform on a window, and then you slide the window and do it again. But this is like n log n operations every time you slide the window. But then there's like the iterative method where you're just like accumulating the values like in these oscillators, and so this is actually less computationally expensive. But this is like standard. The only other thing is just that then the spikes broadcast the coefficients, and this is also like pretty efficient because you only need to, it's basically because of like Nyquist sampling, you don't need to broadcast the coefficient more frequently than the oscillation frequency. And so basically then the resonating fires neuron spiking mechanism only sends a spike out once per cycle. And so then just in terms of bandwidth, it's pretty efficient of communicating the coefficients as well. So like, yeah, I mean, but maybe there's like more, I think this makes it pretty ideal for like being in an online situation and sort of, you know, just dealing with sensory signals online and low latency kind of situation. But I mean, you could probably make the argument that like offline, yeah, there's like more conventional computing things could be a lot more fast or efficient. Yeah.
Okay. Thank you.
Yeah, of course. Thanks for joining.
Any more questions from the audience? So let's see.
So Paxon, yeah, another question. Have you had any thoughts about how you would do cleanup memory?
Yeah. Yeah, definitely. I mean, but this is just, you can do this with the normal dense matrix product. Or if you want to like make an attractor network, you can do this already. Or you can make a TPAM if you want to do it in the spike timing code.
Okay.
Yeah.
Will there be when you release the code, I mean, are you going to give some examples of how you? I mean, cleanup memory is clearly a key component of any VSA architecture. So, are you going to give some examples of how you would implement cleanup memory?
Yeah, for sure. Yeah. So the code, I mean, yeah, I'll have at least like the sparse binding demo and the spectrogram, motion processing. We're going to have a little nonlinear classifier demo, and yes, they all use cleanup memory, but that's just like it's just going to be a normal dot product mechanism. That's just kind of already present. So I didn't really go over that. Yeah.
Okay, thanks.
Again, quick question about normalization, Paxon.
Yeah.
Yeah, so you're putting a lot of effort into that, and so the normalization you've got is, as you're saying, it's the classical linear algebra normalization. You're dividing by the norm, calculated over the entire vector. But it
Right.
seems to me there's sort of a continuum of this, that at the other end, you've got normalization calculated per individual element. So in complex valued, you can just restrict the magnitude of each element to be 1.
Yes.
So
Yeah.
you could, so obviously you've got intermediate kinds of positions as well. So you could divide up your vector into some number of smaller blocks of elements, and calculate your normalization. Is there any advantage or point to doing that in terms of something you care about in this architecture?
Yeah, totally. Actually, very, very, very much so. Yes, like one. I mean, yeah, I mean, doing a phasor projection, doing anything local, like that's easy. Like, yeah, if you want to just do a phasor projection, I can just put that in the Neuron microcode program, no problem. But then of course, the issue with normalization is the connectivity. So you still need to take, this big population of neurons and feed it into this normalization vector, and then spit that back out into the big population of neurons. And the fan out is limited. So like you can only fan out, I don't know, a couple of thousand synapses, right? And so then with just one neuron, you could only normalize, say, like a vector of 2,000. But if you could structure it with the block code or something, or just, you can just, subdivide it and then have multiple. What's nice about the block code is you could just almost do it independently per block, right? But if you really wanted to do a proper normalization on a much larger vector, you could subdivide it and have each chunk of it kind of go to a single neuron to deal with the fan out limitation. But then you would then need these inverse neurons to maybe talk to each other too, to make sure that like they all agree. And then in this way, so if you added some intermediate structure, you could hopefully get around the fan out limitations of the chip. Yeah.
Thank you.
All right. Looks we are done with the questions. No, I see Antonella unmuted himself. So
yes, this is not a question, but thank you, Paxon, for the interesting talk. I just want to mention that as you may already know, I have organized a workshop in the DATE conference that will take place in Antwerp in the middle of April, and the deadline for the submissions has been extended by 1 week, and we will have also invited speakers. So I will be very happy to see you there and to join. I will send you the link in the chat, but it's already on the Google group, so I will not spam it further.
Okay. Yeah, I'll look into that. Yeah.
all right. Paxon, thank you very much for being with us and giving this great talk. And
Great.
thank you all for attending. So stay tuned, and we see each other in 2 weeks from now.
All right. Thank you, guys.
Thank you.
Thank
Bye,
you.
everyone.
Bye-bye.